Hi scholars, let's prove the composition of two continuous functions is itself a continuous function. To start, let's discuss the result visually. What we are going to be given in our proof is three sets, x, y, and z. We will also have a point x bar that is in x. To make our notation concise, here we will label f of x bar as y bar and g of y bar as z bar. We will also have some positive epsilon be given, which will be used to define a ball around z bar. This is shown here in light orange. By the definition of continuity, for the proof to be complete, it suffices to show there exists some positive delta such that if we make a ball about x bar of radius delta, then applying successively f and g to any point x in this ball will give us another point in the epsilon ball about z bar. Here this is shown by the red dots being mapped from the delta ball to the epsilon ball, and the g followed by a circle and then f just means we apply f and then we apply g. Now, we can use our knowledge that f and g are continuous. First, since g is continuous, we know, by definition, that there is some positive number, which we can call tau, such that if a point y is in the ball of radius tau centered at y bar, then g of y is in the ball of radius epsilon about z bar. As before, here we show this mapping from y to g of y with red dots. Similarly, since f is continuous, there is some positive delta, such that if x is in x and within delta of x bar, then f of x will be within tau of y bar. Now, if we combine these two inequalities, we get precisely what we wanted. Check it out. First, I'll put a red dot for x inside our delta ball. That corresponds to this inequality shown. If I apply f, I'll get another red dot, which is inside the tau ball, which again corresponds to the inequality I just added. Doing this one more time with g, we get a final dot that is inside the epsilon ball. With that, the desired result has been obtained. Let's put this together in writing. To prove the composition is continuous, we show that it is continuous at an arbitrary point in its domain. So, we say, let a point x bar in x be given. What I like to do in proofs is explicitly state the definition of what I need to show. Here's what I mean in this case. I will write, it suffices to show the composition of g and f is continuous at x bar. To do this, let epsilon greater than 0 be given, and then it suffices to show there is positive delta such that for all little x in x, if the distance between x and x bar is less than delta, then the distance between g of f of x and g of f of x bar is less than epsilon. Doing this clearly identifies the goalpost for our proof, and it helps guide the reader. With the stage now set, let's leverage the continuity of f and g as we did in our diagram. We can say, by the continuity of g, there is positive tau such that for all little y in y, if the distance between y and f of x bar is less than tau, then the distance between g of y and g of f of x bar is less than epsilon. Similarly, we can write, by the continuity of f, there is positive delta such that for all little x in x, if the distance between x and x bar is less than delta, then the distance between f of x and f of x bar is less than tau. Now, I want to note something important here. When I have taught this material in the past, I have seen many students fumble writing proofs over a subtle detail here. The ordering of the first and the second statements is important. We need to state the result for g and then say it for f. This is crucial because we cannot write the statement for f first because the term tau wouldn't be defined. And it is only after terms have been introduced that we can make use of them. In this case, the step for g introduces tau. Thus, it must be stated first. Alright, with that out of the way, let's combine these inequalities to see that for all little x in x, if the distance between x and x bar is less than delta, then the distance between f of x and f of x bar is less than tau, which implies the distance between g of f of x and g of f of x bar is less than epsilon. That completes the proof. That's all for now. If you enjoyed the video, please like and subscribe. Cheers!